Thank you for everyone joining today's seminar. And before we begin, I would like to make the line acknowledgement that Wilfrid Laurier University acknowledges that much of our work takes place on the shared traditional territory of the neutral Anishinaabe and Haudenosaunee peoples. This land is part of the Dish with One Spoon Treaty between the Haudenosaunee and Anishinaabe people, and symbolizes the agreement to share, protect our resources, and not to engage in conflict. So today's seminar presentation will be given by Dr. Sebastian Jaimungal. He is a full professor and current chair of the Department of Statistical Science of University of Toronto. He is also an associate member and visiting academic at the Oxford Mann Institute of Quantitative Finance, University of Oxford, and a fellow of the Views Institute for Research in Mathematical Sciences. He previously served as the chair of the SIAM Activity Group on Financial Mathematics and currently sits on the editorial boards of the ASA Data Science in Science, the SIAM Journal on Financial Mathematics, Quantitative Finance, and the Journal of Dynamic and Games. Today, he will share his insights on projections on Barycentres of Stochastic processes, and we are incredibly fortunate to have such a distinguished scholar and leader with us today. So please take it away.
Great. Yeah, it's a pleasure to be here at Wilfrid Laurier. It's been a long while since I've been here last, but it's certainly a pleasure to be back. And thanks to all those online as well as for the organization of this seminar series. Today, as the title says, I'm going to be talking about projections and barycentres of processes. This is really part of a 4-paper series. I'm not going to talk about all 4 papers. That's far too much in an hour, in 2 hours, and 3 hours. So what I would like to do, though, is give some of the key ideas that and insights from these papers. And it's going to focus mostly on the one on the very left here. So there are 4 QR codes. You care to scan, you'll find some of the papers. And this is joint work together with my collaborators, Silvana Vicenti at the University of Toronto, Emma Kroll, who's a former PhD student who is now at the University of Copenhagen, and Leandro Sanchez-Bedingport, who's at Oxford. Okay, so what's the setup of our problem formulation? So, okay, great. My pointer is not working. Let's see. There we go. All right. So the setting that we want to think about is the setting where you have multiple models that have been handed to you. Think of them as being handed to you from experts. And these models take the form of some sort of stochastic process. In particular, we'll eventually talk about how these are probability measures on path space, but just think of them as a sequence of models from data. And this data may be different data sets related to the same system that you're trying to analyze. They may come from different time periods if there's some sort of changing regimes or heteroscedasticity of the data over different time periods. They may come from different modeling teams, so different experts that are looking at this, perhaps estimating these models in a parametric way. Some of them maybe within one family class, another within another family class, and a third non-parametrically. And what we would like to do is that, of course, each of these, they produce different predictive distributions over path space or over the sequences of points that you observe. And what we would like to do, the goal of the project, is how can we construct a single coherent model from these collections of models? That's the formulation. So big picture idea of what the question is that you have multiple models given to you from experts, and you want to combine them in one coherent manner. Okay. Now, I'm going to go on to the next slide, which mathematizes it a little bit, and then I'm going to zoom back out and talk at a higher level, and then zoom back in. So more particularly, this is the formulation. We have K experts, K models, or I should say K experts that come with models. They provide you these probability measures, PK, that describe the actual evolution of the whole process. We'll get into some pictures so you can get the intuition in a minute. And in particular, the way that they provide these models to you are in the form of some stochastic differential equation. So each expert provides you a different drift for this underlying stochastic process. This is some d-dimensional object. And the different probability measures dictate what Brownian motion is used here. Now, for those who aren't too familiar with that terminology, don't worry, you'll be able to understand the gist of it as we come up. And as I said before, we want to combine these into a consensus model. So here's, and one other key aspect, the projections part. Not only do we want to take these different models from experts and provide one consensus, we would like to incorporate certain beliefs or preferences that the agent who's combining the models has. Now, these beliefs or preferences could come from exogenous regions. For example, maybe you've got a bunch of models that are modeling climate, and you wish to use it to evaluate the risk associated with, I don't know, some clean energy project. Okay? And the regulator tells you that whatever model you do use, you should ensure that over the next 20, 30 years, the average temperature increase is, I don't know, 2 degrees or 3 degrees, whatever the regulator tells you. And maybe the average time that the temperature spends below some sort of linear line is only 10% of the time. So in other words, the regulator is imposing this preference onto you for a model that you're going to use for other purposes. How do you incorporate that information, that preference, that belief, because it could also just be personal. So what do I mean by personal? Maybe you're modeling financial markets and cryptocurrency. You're looking at Bitcoin prices, and you would like to develop some risk mitigating strategy for Bitcoin. And you've estimated a bunch of models for Bitcoin over the previous month, the month before that, the month before that. You have 12 different models from the last 12 months. You want to combine to a consensus model, but you also want to incorporate the fact that you believe that the time Bitcoin should be always between 90,000, 95,000 over the next month with a 90% probability. None of those models have that property from the history. The historical models don't satisfy that constraint. But you want to make sure that you generate a model that has that constraint so that then you can develop some trading strategy or utilize it for whatever reasons afterwards. Okay? So you want to impose, you want to project the models onto this phase of constraints. Okay? So we're doing these two things simultaneously. So here's an example. So now, again, you can forget the math and just look at the pictures. So this is an example of an expert model one. Think of it as a climate model, if you will. Forget about the time scale on the horizontal axis. One is 30 years, let's say. The vertical axis as well. One is really 3 degrees. Okay, if you want to map it to something like that. What you see here is a sample path in blue from this underlying stochastic model that has been given to you from expert one. The shaded areas are quantiles at every different point in time. And the shaded lines that you see there, these are other sample paths. Now there's a dotted red line and a dotted black line. Forget them for now. So this is model one. Now another climate expert says, actually, there's going to be some sort of long-term cyclical effect. That's hard word to read. Some long-term cyclical effect where there's a bit of a heating and a bit of cooling, and a bit of heating that's happening on some larger timescales, and the actual sample path should instead look like this. Okay, these are two different experts. Maybe you believe them equally well. Maybe not. Maybe you say that actually expert one is much more trustworthy. They're using a much more sophisticated physics model to generate the underlying stochastic process. And so you want to put a large weight on that model one. Or maybe it's model two that you want to put large. We're agnostic as to how you come up with how much you believe the different experts. Okay? So you can do this. I mean, what one canonical approach could be take the two models and then compute the posterior probability that those models have explained the data in the recent past, right? And then use those as your beliefs in those models. Okay, so I did a fun little experiment in the age of AI. I said, let me feed ChatGPT model one, model two, And I said, please combine these models to produce one model. So what do you think it did? Huh? Average. So this is what it did. It put them side by side into one model. Okay. So then it said, okay, that's not what I want. I want a single model that evolves over time from 0 to 1 in a single plot. Please generate some words like this. Then it did this. So what did it do? It sort of basically overlaid the two models, one on top of the other. And we kind of laugh at it. But actually, if you think about it for a moment, yes, the ChatGPT is not doing something intellectually deep and realizing that this is what it's doing by merging these images, but you can interpret the merging of these two images as making a mixture model of model 1 and model 2. It's as if you say, there's a Bernoulli random variable. When it comes up 0, model 1 is correct. Simulate from that. When it comes up 1, model 2 is correct. Simulate from that. And if I simply had a model which is a mixture of these two, I would actually get paths that look very much like that. Of course, the quantiles are wrong, right? But the paths, the set of paths that I would get is more or less correct. Okay, so I'm going to show you next what our methodology actually does. Now, before going to next, let me explain now these dotted lines. So the dotted line here, this red dotted line, is a line where I would like on average the process to actually at time 1 to be that dotted line. And the black dotted line is I would like the process to only, I think, 10 or 20%, we'll see in the next slide, be below that dotted line. So of course, neither of these two models, I'm putting them side by side here, neither of these two models satisfy that criteria, right? Those constraints, they do not. You can see clearly model 1 on average is much higher, model 2 is on average lower, and the amount of paths that lie below this black dotted line is, I don't know, maybe 50% approximately, and over here it's actually higher. So they don't satisfy this constraint. Here's what happens when you use our theory, our methodology. It generates sample paths that look like this. It's a blend. It's a consensus between these two models, and it's distorted in such a way that it maintains that those two constraints that I said. So the expected value of the process at time 1 is exactly 1, and the amount of time that it spends below that dotted line, which is the expected value of the indicator, the integral of the indicator, is 0.2, 20%. So this is the kind of thing that we would like to do. And I'd like to tell you about the mathematics that leads to model combination, this using the KL geometry. Okay. And if you look at this problem, so maybe KL, maybe I see some students, some undergraduate students in the room, so perhaps that's not completely familiar to you, but the KL is a way of measuring a type of entropy, it's a relative entropy, if you will, between the two distributions. And what it exactly is, if the distributions were discrete, it would be the sum over all outcomes of the probability under Q of that outcome times a log of the probability out of P divided by the probability of Q of that outcome. So it's this weighted log of the likelihood ratio between the two probabilities. So for discrete distributions, you can do that. And you can compute this analytically. Now, what happens when you do this for random variables is you get the following. You no longer get this kind of bimodal nature. You get a true blending where the distribution slides over from having a small variance and shifted and kind of mean to the left, and a larger variance with a mean to the right. Now, it turns out for Gaussian distributed random variables, each one of those intermediate consensus models is also Gaussian, but that's just a special case. It is not true in general, and it's not true for when we lift this to path space. Okay, is the intuition, does it make sense? Everyone's okay? Questions?
So do you need to specify the weights?
Yeah, so as I'm changing these pictures, the weight's changing from that's one.
That's a sort of a user.
That's a user input.
Okay.
It's a user input, exactly. How much do you believe the different models? And I just said one canonical approach to studying phi is to say, okay, I have these two expert models. I have some data of my own. Let me assume a prior distribution of equal weights on those two models that have been given by the expert. Compute the posterior probability that the data is generated by model one, and one minus, of course, in model two. I use that as my phi. And maybe I bias it because, again, I believe that expert one has generated this model with 10 times more data than expert two. So maybe the factor should be 1/10. Right? You can use any methodology that you wish to come up with the pi's. That's an input. Yeah.
So why could what are other ways?
Yeah, you could use other divergences. So we have theory on when this is chi-squared. We have theory on when this is Salas or Renyi. So variations of the story go.
And also symmetric theory, right?
No, the symmetric version is much trickier. So why? Okay, that's a good question. This version, this is the forward pullback-Leiber divergence. This is convex on the space of probability measures. The reverse is not. So if I sum the two things, I get a functional on the space of probability measures as not convex. So I have no uniqueness, no existence. In discrete settings, you can explicitly calculate, but in the general path space, uniqueness existence is lost. So there's a good rationale as to why I use this one. Yes, I don't know who's first. It was about simultaneous. Go ahead.
Does the KL score words when we have more than two components, more than two distributions?
So there's a capital K here. This is overall however many models you wish. The minimizer of this still exists and it is unique for the random variable. And I'm going to show you for the original problem that I posed on processing incidents, which also exists. Yeah.
There's a question online about what is the class C restricted to?
Yeah. So I will talk about the restriction later, but it's basically those constraints of those beliefs that I was mentioning that the agent may have. In this random variable case, maybe, for example, it is that the expectation under the consensus model of this random variable should be, I don't know, 0. Let's say that would be a constraint example. Or the second moment is something, or the conditional value at risk is something. These are all constraints that you can incorporate in using this methodology. Okay, so now I think I'm going to switch back a little bit to the mathematization of the problem. And we will have a few more mathematical slides, and then I'll switch back again to some applications. So the posing of the problem, it's the same as in the previous. I think I used dk out here instead of just k out. Doesn't matter. So this is the minimizer. We're after we actually don't know a priori, does a minimizer exist? So argument is a bit, I'm jumping ahead, okay? Really, I should be looking at the inf, and then I should ask the question, is the inf attained? And then proceed, okay? So we're looking, I'm telling you that in fact it does, so we do in fact have an argument. So we look for the minimizer of all probability measures of the weighted KL, and the way it looks is something like this. What we're going to do, we have these different probability measures, and remember again, these are on path space in the general setting. They're not just, univariate or multivariate, finite dimensional random variables. It's really on the paths of stochastic processes. What turns out to be useful in our study is an intermediate probability measure, but I'm going to call this phi mu bar. Now, what is that? This is a whiteboard here, yes?
Yeah.
So I can write something so that you can remember the underlying dynamic. looks like this. Okay, for under the K probability measure. So this is a Brownian motion under the probability measure pk. An expert K tells you this. So they all have potentially a disagreement on this drift. Like if I replace this drift with the average drift, and I introduce a new object that I'm going to call W bar, which is a Brownian motion under some probability measure, which I call Q mu bar. That's what this Q mu bar represents. It represents a probability measure under which the dynamics of the underlying process simply has the average drift. It's what you might naively think would be the correct consensus model. It's wrong. It is not. But it is a useful intermediate object that helps us analyze the problem. Instead, what we're after is this barycenter. So QB, think of it, it is the minimizer of. And the constraint set, so what we really want is this QB. This Q mu bar is intermediate, plays an important role, but not fundamental. Okay, the constraints are of the following form. This is an example of the kinds of constraints that we can take any function of the stochastic process at the fixed terminal time, make it vanish. Okay, so you tell me what the F is, and I will give you a model that's inside this constraint set. As well, you could have a running constraint, so I can have the expected value of the integral of some function of the process vanishing. In fact, you can generalize this far more to be something far more general, and you could use any F capital T measurable random variable that's a function of the path. Okay, but these are kind of canonical examples. This is exactly the kind of example that we saw the pictures of earlier. I have to go back a little bit more. Okay, maybe too much, right? This here, this is exactly of this type, right? The expected value of the process at time 1 is 1. Put the 1 on the other side. My F of X is X minus 1. Okay, same thing with the integral of the indicator. Put the 0.2 on the other side. My G is the indicator minus 0.2. Okay, so we can work with models of that, or sorry, constraints of that sort of expectation type constraints, but they can be arbitrary functionals of the entire path. Okay, so again, I'm going to continue a little bit. As I said, this average drift measure plays an important role. That's what I mentioned here, right? You take this drift, the average drift, this plays an important role, and X has that dynamics. Okay, now this may be more just for the experts in the room, but the way that we solve this problem, this one here, the way that we solve it is that here you're looking at probability measures on path space. So instead, we parameterize those probability measures on path space by using stochastic exponentials that are driven by arbitrary ethical processes. This allows me to parameterize all possible ones. And what we prove at the end of the day is that restricting to this particular class is not restrictive. The minimizer has to live in data. Okay. So we actually show that there's unique consistency. So why is this a useful set of probability measures? Well, it is a useful set because by construction, under the probability measure Q theta, the drift of the of the X process is theta. It's just a canonical way of parameterizing. What we show is what we then do, if you've ever taken any optimization course, if you're trying to minimize some function to constraints, a nice way to do this is to reduce a Lagrangian, right? Where the Lagrange multipliers help to enforce those constraints, right? Assuming that the Slater conditions are satisfied and so on, right? So we prove that. This is the Lagrangian associated with our constraint problem. So our constraints are sitting here, and this is our KL divergence here, or weighted KL. Now, because of this stochastic exponential form that we're parametrizing the alternate models, you can rewrite that KL term contribution in terms of this sort of quadratic kind of a quadratic loss in quadratic in the alternative drift of the asset. Now, I'm not going through all of the proofs here. I'm just going to give you the main theorems. And as I said, we're going to come back to some applications in a bit. So for those non-experts or those who are finding this a bit challenging, don't worry, we'll get back to something tangible. When this eta is zero, when etas are zero, then these two terms are gone. And what you're after then is simply finding the barycenter. When they're there, you are finding the constrained barycenter. In other words, you're projecting the barycenter, or I should say, you're projecting the original minimal KL onto the constrained set. It's not clear that that's the same as start with the barycenter and project to the components. That's not obviously the same. Okay, so what we show is that the value function, this is kind of like a score that comes out of this. It's a score function associated with this Lagrangian. It has this very unusual form. Now, the details of the formula aren't so important, but one ingredient I think is this object that shows up here, which is kind of an exponential tilting or exponential reweighting, is composed of the following. It has the following structure. It's the deviation of model K from the average, weighted by the inverse of the instantaneous covariance. Right? It's kind of a norm, not an L2 space, not Euclidean norm, but more or less a Mahalanobis-like distance. However, it's a Mahalanobis distance across models, which is a very unusual thing. Okay? It's not something that naturally shows up in other settings. So this is a weighted Mahalanobis distance across models. And the way we can think of this as it penalizes models that deviate too much from this kind of naive consensus model in regions where the instantaneous covariance is small. So if the instantaneous covariance matrix is small, the model should agree. And if they don't, then we sort of penalize paths that go into that region. That's a way of interpreting what this thing does. The key result is that, or I should say one key result is that the likelihood ratio, or the Radon-Nikodine derivative, between the naive consensus model and the barycenter is exactly e to the negative this bar sigma object. It exactly tilts you away from those regions where the models disagree and variance is small. And in this way, it is using somehow the geometry of the Kullback-Leibler divergence, the metrics, or not metrics, but the divergence that's introduced by it, as well as this instantaneous covariance. So this is one of the key mathematical results. We have uniqueness, existence, and this is what characterizes that barycenter. Moreover, if we wanted to impose the constraints, we have to have one more assumption. There's a feasibility assumption. So what do I mean by that? Let's say it's over here. Let's say I have two models for the stochastic process, model 1, model 2. This is time 1. It's time 1. Let's say model 1 produced paths that kind of end up with probability 1 in this region here. Okay? And same with model 2. They end up with probability 1 in this region here. Well, there is no way that I can introduce a distortion of these models such that the expected value of x at time 1 is 10. Okay, well above that. Because there are no paths that do this in the underlying models. So this feasibility constraint is a way of mathematizing that condition. And it tells us that you need to look at the gradient of the logarithm of the, or I should say the gradient of the cumulative generating function of the constraints under the barycenter model, and there must exist a point at which this vanishes. And if there exists such a point, we know that we can prove that it is unique. Okay. And that's this eta 0 star, eta 1 star. That's a feasibility. And if such a thing exists, then we have this beautiful, what I think is a beautiful formula for the optimal drift. So what does it look like? Mu bar, as I said, is that consensus model, naive consensus model, just average the drifts. you must correct it by the gradient of the log of something. This is suspiciously similar to some sort of score, right? Scoring function, and that's what this is. This is a scoring function that determines that I should say penalizes paths that deviate, or where the models deviate too much from one another. So this is our optimal constraining barycenter. Now I think the next slide is okay. That's the change of measure. It just tells us how it looks. One last technical slide. Forget the slide. Go to the picture. I said the following thing at the or a few minutes ago. I said it is not obvious that if I take the weighted KL and I project on the constraint set, I get a point. Now take the models, minimize the weighted KL, I get a barycenter, and I project onto the constraint set. It's not clear that those two things coincide a priori. This is highly nonlinear space and so on. What this theorem says in this picture version is that this diagram is commutative. In fact, they do coincide. If I take the minimum weighted KL of a collection of models and I get a barycenter, and then I project onto the constraint set, I get the measured Q star, or alternatively, if I just minimize directly the weighted KL subject to those sets of constraints, I get that same Q star. So in other words, this, like find the barycenter, project on the constraint, is the same as just projecting on constraints and minimizing weighted KL. That's a very nice mathematical result. Okay, I think I have maybe what, less than 10 minutes left?
You should still have 20.
Oh, okay, yes.
Which of those paths is easier to do?
Mathematically, they're about the same.
Okay.
Yeah, I mean, well, the theorem tells me that they're the same, and
Well,
if you look
end
at
result's the same, yeah.
yeah, the end result's the same. So if you look here, this is the Q theta eta star, which is the optimal measure relative to the naive consensus model. It's made up of two components. Look at this exponential. It factors into 2 bits. There's the exponential of just the negative integral of this weighted Mahalanobis distance across models, and it has the constraints there as well. If I separate those into 2 things, I can view it effectively as first change to the barycenter, which is given by this, then project.
Yeah.
And because the exponential splits in this nice way, that's kind of why the diagram is commutative. Yeah. Okay, now I think I have some examples that I want to show you. Okay, right. So we talked about these 2 models in the beginning, right? Model 1, model 2. And here is what I'm going to do is I'm going to show you how the blending, how the consensus model changes as we change the weight of the expert on model 1. So pi 1 is a weight of how much we associate to model 1. This is 0.3, 50%, 70%, 90%. You can see it starts to inherit the characteristics of the different models as you put more weights on it, as expected, while all the time ensuring that the constraints are satisfied. So for each one of these constraints are satisfied. They are distinct models, but the constraints are all satisfied. Now, you might ask, how do we use this weird, this distortion object here to get those kinds of sample paths? Here's one naive way to do it. Very simple way to do it. Simulate from the naive model. Simulate from this one where the drift is U bar. Okay. And then simply compute these objects along the paths that you've simulated. Now randomly select from that collection of paths using this weight as the probability. Instead of 1 over, let's say, the 10,000 paths, instead of every path getting 1 over 10,000, path 1 gets whatever this exponential thing is, divided by the average of all of them. And path 2 gets, again, whatever that exponential is. This is one way to do it. So you just go ahead and you simulate from this model and you generate like this. Alternatively, if you wanted something that is more analytical, if you will, is you use this formulation. You need to compute this conditional expectation under this naive model of this object. So if you can do that analytically, and in some cases you can, such as if all of these models are affine models. Now, a lot of you know about these so-called generative AI diffusion models. So the forward process in these are almost all affine. They're just Ornstein-Uhlenbeck processes. Now, the reverse process isn't affine, and that's the one that you really want, but you can still utilize some of the techniques here to give you approximate solutions from that. Another way is you can say, well, I need to estimate this function for all t and x. So how can I estimate that function? If you look carefully at it, what this functional is, just treat all of this exponential as some big random variable. Right? It's effectively kind of a big random variable. And I'm computing the conditional expectation of that random variable. So you can use the L2 projection result, project onto ft measurable random variables, and I will estimate this omega. How can I project onto ft measurable random variables? I can use deep learning. I can parameterize omega tx as an arbitrary function of t and x using neural networks. And then I can compute the L2 error between omega t x at time t and this big object that's under the expectation. And I minimize the L2 error. That turns out to be exactly, by definition, using elicitability, the reasonable expectation of that object. That's under the assumption of Markov strategy. Okay, so this is a Markov setting. We have generalizations for non-Markovian. So there's a little link down here about a deep learning approach that if anyone wants to ask about it, I can go into it. But that's the essential idea. The deep learning approach is using the neural networks to approximate an omega function that I just pointed out by using this idea of elicitability and L2 projection. Okay, maybe I will skip this and instead go to another application. So here's an application. I know that there's a number of people doing sort of financial math. And even those that aren't, this is a nice application that's easy to understand. Imagine I gave you data that is supposed to represent functions at every point in time. So the object that sits here is something called implied volatility. It's irrelevant. Okay? So the data are these red dots, dot, 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 dot. And the orange is this is another set of red dots. That's on another day. This is another set of dots. That's on another day. And what I've done is I've taken the raw data, which is discrete on every day, and I've projected that data onto a functional basis. Okay. So I've taken Legendre polynomials, and I've found the coefficients of the Legendre polynomials that minimize the L2 error between the data and this expansion onto the Legendre polynomials. So I'm doing functional data analysis. Okay. Now, so that's what's written here. I find those coefficients onto a fixed set of bases across every single day. And then I learn a neural stochastic differential equation for the evolution of these coefficients. What's the connection with what we just did? Well, these A's are our X's. Our data is infinite dimensional because it's a function, but we've projected onto a finite dimensional basis, the Legendre polynomials. That gives me my X's. And then I've learned to model for those X's using neural estimates. And we can do this for 3 different time periods. This is an example that I'm going to show you. I take 3 different time shots, and I learn the model in these 3 different time shots. I learn different models. And this is an example of what the coefficients look like. So there's an interesting time series evolution there. You can see all sorts of interesting patterns in this thing. And the neural SDE is able to capture this quite well. We've developed some methodology for doing this type of work for implied volatility surfaces. If your data is actually a 2-dimensional surface as opposed to SMILE, and utilizing a model misspecification corrector called the probability integral transform. But those are sort of details on making this method better. So we have this 5-dimensional time series, and then, as I said, we learned 3 different models. I guess the first 1,000 day, the next 1,000 day, and the final 1,000 days. And then I've imposed a very odd constraint. So this is a little hard to digest, but let me draw a picture, another picture, and it'll be obvious. So as I mentioned, what we're generating is a model for the dynamics of a curve. Right? So what evolves through time, at every snapshot in time, you actually get a curve. You get some sort of curve, right? It's every single snapshot in time. And what these coefficients are here tell me how to expand on this basis. So this is fixed. This is the thing that's evolving through time. As a function of delta, therefore, I get fluctuating curves. The constraint that I'm imposing is a straight line. I'm saying I want at after 1 month, I'm going to look at the slope of this curve here. And I want that slope on average to be 0.05. Now, imagine trying to construct such a thing before without using any of this technology. You have a model that gives you the evolution of curves. I want you to distort it. First of all, I want you to combine multiple models of such type. And secondly, I want you to distort it so that the slope at that midpoint is exactly 0.05, or I should say is 0.05 on average. That's a very challenging thing to do, but it falls directly within the setup we have. For those in the financial math, quant finance, financial engineering field, you will recognize this as saying, I want the skewness of the curve to be of a particular value. That's what this constraint does. And I can make it even tighter by saying that I want the skewness, the probability that the skewness is in a particular range to be very high. Right? I can do that, and you'll get distorted things. So this is a way of distorting the models to do this. And here's a simulation of these curves. So focus maybe, first of all, just on the purple curve. The purple one is the one that's kind of going up here. You notice that it's sort of deviating from all the other ones. What are all of the others? Well, the blue one is the evolution of what model 1 gave us from estimating data over the first 1,000. The orange is from the second 1,000, and the green is from the third 1,000. They kind of go somewhat close to one another, right? The blue, orange, and green, they're somewhat close. The purple pulls away, and then you might say, well, this is a garbage model, right? It's pulling away from what we've seen happening. Well, that's not right, because we have specifically requested that under this perturbed model, we are projecting onto the set of paths such that, on average, the skewness is 0.05. The slope right here is 0.05. And if you look at the regular evolution of the other curves, these skewnesses are too low. So the methodology worked that it had to push the paths into a region where we get that higher skewness. And from those other models, the only times in which you get this higher skewness is that the overall level was also high. So it correctly is incorporating all of those constraints and the evolution that we would like to have. Okay, I think I'm going to stop there. I think that's a good point to stop, and happy to take questions. As I said, there was another paper that I knew I wouldn't have time to talk about, so I'll stop there and say thank you for your attention. Very happy to take questions about this or any of the other works.
Yeah, because you have a constraint here that basically, like in all your models, the volatility function the same.
Correct.
Yeah, because of the example you showed with two normal distributions, that was the opposite, right?
No, well, with normals, you see, I can have a stochastic process such that terminal distributions have different variances.
Yeah, I mean, like, yeah, you could use
Yeah,
stochastic.
Right, so the terminal variances can have different. There's a way to incorporate different volatilities here by lifting this to a higher dimensional space
Yeah.
where there is a stochastic volatility factor for all experts, and expert one believes that that stochastic volatility factor mean reverts to different, or I should say, the different experts expect that they mean revert to different levels. This is a way of incorporating different volatility. So it's not exact. It's not like I can get arbitrarily close to what you want, but not take the limit.
There was a question from online
Yeah.
earlier. The person asked, how do you decide what Q is? Is it just a power that you increase to shift the barycenter? Or in other words, can you make an educated decision on what the Q might be in order to get the barycenter to a particular point?
No, so the Q is what we are seeking.
Yeah.
Right. So Q is actually the object that we are seeking over. So we're not we're trying to optimize that Q to minimize this weighted K out. So it's not like we're just distorting the probabilities by raising them to a power Q. It's a completely different, much more general way of distorting. Yeah.
So I'm just, yeah, I'm kind of curious. You have different random motions on the different probability measures.
Mhm.
And at the same time, you have different drifts.
That's right.
But using change of measure, you can change the drift. Right?
That's right.
So why do you need kind of to change two objects? Because you can have the same mu and sigma, but
Well-
different random motions.
Well, because I'm viewing it as I am modeling the same system. X has to be the same. So under probability measure 1, X evolves with some Brownian motion W1 and has this other drift V1. But under probability measure 2, it has a different pathwise dynamics, but it's the same X process. So this is why we change them both. You can, of course, write everything in terms of one single probability measure. And that, as I said, that's a trick that we use, this mu bar, there it is, right? We use this intermediate probability measure as a way of putting everything under one roof to start with. Yeah.
So basically the assumption that WK is under the case is more technical, right? I mean,
It's
you're not really kind of
Yeah.
using that, right? Because the main factor is the drift.
That's right. The main factor is that the drift is the thing that differs between the different models. It's technical so that you use the same probability space, but different probability measures.
When you show the diagram, like what about
Cumulative one?
Yeah, cumulative one.
Mhm.
What about the other approach when you project all the measures on the S space?
You project the P's first and then find the minimum K.
Yeah.
I do not believe, I don't have a proof, but I do not believe that that commutes. I believe that if you project each P onto the constraint set, you'll get a bunch of, let's call those Q1 star, Q2 up to QK star. These satisfy the constraints, but the consensus model may not. There's no reason to believe that they will.
So it's a kind of too constrained to find that kind of with the same, right?
Yeah. I mean, an interesting question could be, how close is the consensus model by first projecting the individual experts onto the constraints or to the true consensus model that's directly projected or through the Barycenter? Yeah. This I don't know. There must be some. I think we should probably be able to characterize that. But my strong suspicion is that gap is not zero, unless it's really specific, really special case. Yes.
What's the computational cost? I mean, the consensus model.
It's so if you use the quote unquote naive method of simulating, so as I said, let's say you simulated paths from this one single model. So however costly that is, then you just calculate, you approximate this integral by a Riemann integral along those paths. And now you just have for each path, you have a new number, a new weight, and then you resample from that. That's very efficient. That's super efficient. It's not exact because you are only taking a finite number of samples from the naive model to approximate this likelihood ratio, right? So it's going to be approximately true, but it'll get you there very quickly. The longer approach using the deep learning thing, well, we all know deep learning approximators, they work, but they churn, right?
So as long as you use the faster way, if you keep getting more models to integrate into the consensus, it would be easy to keep this thing kind of online and updated as you.
Absolutely, yeah, and it would be very easy to change the weights as time goes by, right? If you generated samples from where you had a certain belief, 10, 10, 80 in these three models, and then you've generated, now you've gotten some more data or some other information, and you distort that, you can run it really fast to change it. Because you can keep all the paths that you generated. Actually, no, you can't, because a mu bar would change, right? But still, that's very fast simulating from SDEs.
There's a similar question on efficiency coming from online. He's asking if you've done any work towards the number of mixtures going to infinity, so like a very large number.
Right.
Of
So
distributions.
I suspect this is we have to prove this, but if you look at this weighted Mahalanobis distance, and you take a look at how this pi and the different models mix in here, really the correct result should be replace the sum over pi k mu k transpose sigma inverse mu k by an integral over a measure over models. And then the k just takes place, replace it with some index that indexes over the continuum of models. So morally, that should be the correct thing. We'd have to prove it rigorous that in fact taking the limit after doing the consensus is the same thing as doing the infinite weighted k or the weighted k over all models, right? Which is we all know interchanging limits and optimization problems are not necessarily going to go through, but morally, that's what I suspect.
Here you work with the probability measures, right? So like it's a particular class, but the results looks like quite fundamental. So did you think that it can be generalized to the case with general measures and when you basically have
so not probability measures, just measure signed measures.
Yeah. Okay, like barycentre can be defined for.
You can define the barycentre, but of course you have to be careful about the KL because the KL is no longer valid for the signed measures, right? You'd have to use a different, maybe you can use some sort of signed version of KL.
So as long as you can find some kind of metric which is for example convex or so that.
Yeah, the real key is convexity in measures, right? Convexity of your functional over space of measures. And the way that we prove these results is we didn't actually use that in the proof of these results in the first version of things. But now we have proofs where we do actually see why that was so important, right? This was using all stochastic control techniques. But yes, that's an interesting question. Yeah, I mean, I'd love to see, I think that this methodology, this framework of coming up with consensus models and projecting onto sets of constraints has applicability in a lot of different areas in applied statistics. There's a little bit of, I would just say, a little bit of lifting to grasp the concept of it. But as I said, in terms of simulating, if you have models that you can simulate from in this sort of SDE framework, even if it's a discrete version of them, then this consensus approach should work through quite easily and quite efficiently. So I'd be happy to talk to anybody who is curious about trying it out in their own particular application settings.
Yeah. Do we have any more questions? Oh, there's another question from online.
Yeah, please.
So in that infinite mixture setting, do you see any problems starting at mu bar?
Infinite mixture setting. Okay, well,
So this,
okay, what you mean infinite number of models?
Yeah.
You're not doing mixture models.
yeah.
Do I see a problem with starting with setting mu bar?
Yeah.
No, because again, mu bar would be, okay, I don't know if they can see where I write, when I write on the board here, can they?
I think they can. It,
So what is in the discrete setting? It's mu by just sum over k by k mu kt. And what I suspect is that this just becomes an integral
mhm.
over mu, let's say x, or maybe y. Let's say y t, and then this is a measure. So this is like a measure over models, by a probability measure over models, and that's indexed by it. Okay, maybe mu is not the right thing to use because I use it twice.
Yeah.
Okay.
Yeah.
So this is what I suspect happens with the mu bar. And of course, you have to have a way of calculating that, right?
Yeah.
So imagine that your drifts, one way to think of it is, imagine if your drifts for the different expert models is a continuum, is a parametric family, and you have a distribution over parameters in that parametric family. And let's say mu is, I don't know, an OU process with a different mean reversion rates, and you have a posterior probability over the mean reversion rate estimated in some way. Well, that posterior probability is this distribution here, and the y is just indexing the mean reverting rate. And so I could easily compute this object and then simulate from it, because now I'm still only simulating a d-dimensional object where d is the dimension of x, even though I have an infinite number of models. So it should be perfectly adaptable to that situation.
Thank you. If we don't have any more questions, let's thank our speaker again. And we are going to end our Zoom meeting online. Thank you for joining.